Okay guys, so I'm going to go over some aqueous solution problems from the Princeton invite, and I guess I'll just go over go through each one of them, explain the logic. So for this first one, we have silver sulfide, and for A, we have to calculate the molar solubility given the KSP and the Ka. Now this is really similar to the classic calculate the molar solubility problem, with the added bonus of a Ka. So first off, we can just write down the reaction and the equation. And a lot of invites will actually have this be worth a couple points, so it's good to always write it down just in case. And this is 2x squared times x, or also, so that is 4x cubed. Okay, and now we can move on to and deal with this Ka. Now, if you look here, they give us Ka, but we're dealing with a sulfide ion, which means we're in a basic solution and we need the conjugate base. So instead of Ka, we need Kb, and we can find that by just doing 1e negative 14 divided by the Ka, which is 1e negative 19, and that gives us 1e5. So Kb equals 1e5, which equals concentration of HS minus times OH minus over S2 minus. And okay, so now we have both components, and now we can multiply them together to find KSP. So we have KSP equals 80 negative 51. It's really small. And then if we multiply them together, then the sulfides cancel out, so we're just left with Ag plus, HS minus, and OH minus, which is K1 times Kb, and K1 is 4x cubed, and Kb is 1e5, and all of that is equal to KSP. And then now we can just use our calculator and solve for x. So we would do 8e negative 5 divided by 80 negative 51 divided by 1e5 divided by 4, and then cube rooted, and we're left with 2.71 e to the negative 19 molar. And that is the answer to A. And for B, B is actually really simple. So it says calculate the molar solubility of a silver ion, and because the silver ion is 2x, we just multiply x to find the concentration, to find the molar solubility of the silver ion. So it's just 2.71 e to the negative 19 times 2, and that would equal to 5.43 e to the negative 19 molar. And show your work for this one. Yeah, because they'll probably require you to show your work. And yeah, so that is 27. And I'm just gonna go on to the next problem. And okay, so for 28, we have the classic percent change in molar solubility. So I'm just going to do the first one, since the first and second one are really similar. And so, okay, so KSP of yttrium hydroxide is 1e negative 22, and then by what percent does the molar solubility increase or decrease in solution of 0.05 molar yttrium sulfate compared to in water? Okay, so first, we just have to find its normal KSP in water, and you can just write out the equation real quick so you know what you're dealing with. Whoops, I don't know what that was. Okay, and then you have KSP, which is 1e negative 22, and that is 27x to the 4th, and you can now plug that into your calculator. So 1e922 divided by 27. And x is equal to 1.39 e to the negative 6 molar. And that's in water. So I'm just gonna underline that so you don't forget about it. And okay, so now we have the first part done. We found the molar solubility of it in water. Not too hard. Now we have to find the molar solubility in 0.05 molar yttrium sulfate. Now this is pretty much the same concept, except we start out with a certain amount of the yttrium ion, and yttrium sulfate is written like this, and you can see that in every mole of yttrium sulfate there are 2 moles of yttrium ion. So the initial concentration of, so I'm just going to write the initial concentration of the yttrium ion is 2 times 0.05. So it'll be just 0.1000 all y plus. And then now, I'm just going to go ahead and use an ice table for this, but you don't need to. So we have 0 and then plus x plus 3x. We start off with 0.1, so we can just do that. And you don't need to do this at all. It's probably way easier to just go ahead and do it algebraically. But this is just to, like, I guess show like the individual steps if you're used to like an ice table. And yeah, so basically it's the same thing as before. So now we take the KSP and that is equal to 27 x to the 4th. Nope, not x to the 4th, that's x to the 3rd. And because the KSP is really small, we can just go ahead and ignore this x and multiply by 0.1. And now we can solve for x. So that's just 1e922 divided by 0.1 divided by 27. Oh, whoops. Plugged it into my calculator wrong. Okay, so it's 1e922 divided by 27 divided by 0.1. Cube root of that. And we get 3.33 e to the negative 8 molar. And I'll just underline that. And that is the molar solubility of yttrium hydroxide in 0.05 molar yttrium sulfate. And so now we have to find the percent increase or decrease. And we know it's a decrease because the numbers decreased. So we can do percent decrease equals 1.39 e to the negative 6, which is the molar solubility in water. And then we subtract it with the molar solubility in the yttrium sulfate. And all of that over 1.39 e to the negative 6 times 100, and that should give us our correct percentage. And that is 97.6% decrease. And yeah, and that is just like step-by-step way to solve a really classic like percent increase or decrease in molar solubility. Okay, and then we have just a couple more problems left. Okay, does that fit? You can see that, right? Okay, that's fine. Okay, so now we have 29, and it says, and this one deals with a complex ion. So we just calculate the molar solubility of iron 2 antimonite in a 1.4 molar solution of potassium cyanide, and ignore any acid-base effects of SbO3 3-. And okay, now for this one, we first have to determine the K after combining KSP and KF. So for KSP, this is the equation. And KSP equals 4.32, what is it? Okay, E negative 92. And then KF, we have, why do I keep writing 3? Fe2 minus plus 6 Cn minus makes this complex ion, and that KF is equal to 1E24. And so now what we have to do is basically combine these, and then we can do that by multiplying this equation by 3, so the iron ions can cancel out. So if you multiply it by 3, we just multiply coefficients. And okay, and what that does, when we multiply the reaction by 3, we have to cube the KF. So 1E24 cubed, and that is 1E72. So I'll just write and then now we can add the reactions together, so cross those out, and we are left with this is long. And because we add them together, we can now multiply the two K's. We have 1E72 times 4.32 E negative 92, which should leave us with, I'll just write it down here, K equals 4.32 E negative 20. And okay, so now that we have the K, we can basically do the same thing that we've been doing before, except with this reaction. I'll just underline. Okay, so we can have 4.32 E negative 20 equals 3x cubed times 2x squared, if you look here, and then that would be 1.40 minus 18x to the 18th, but because this is really small, we can go ahead and ignore this little x, and then now we can just solve for x. So we have 4.32 E negative 20 divided by 27 divided by 4 times 1.4. Okay, and that should give us 1.76 e to the negative 4 molar. Okay, and that is the answer to A. Oh, I'm sorry if you can't see this. Okay, is that better? Yeah, that's slightly better. Okay, now we go on to B. Now this ties back to acids and bases. So if the Ka of the ion is 6.38 e to 13, calculate the pH. Okay, so first thing we do is write out the equation. And because it's basic, and we know it's basic because it can only accept hydrogen ions, then we have to find Kb. They give us Ka, no biggie. Do the classic. And so our new Kb is equal to 0.0157. And then, so the concentration of that ion would be equal to 2x and we know it's 2x because it's what we wrote up here. And so just like before, we just multiply what we found here, the molar solubility here, times 2. So that's 2 times 1.76 E4. And that equals 3.5 3.53 e negative 4 molar. Okay, and now we have this initial concentration. So now we can just solve for the pH. So 1.57 e negative 2, which is our Kb, equals x squared over 3.53 e negative 4 minus x. And we can't get rid of this x because this is a relatively large Kb, so for that we have to use our solver. And with that we have x equals 3.45 e negative 4, and this is equal to the concentration of the hydroxide ion, which equals 2, which is equal to the concentration of that. So POH is a negative log of what we just found here with using our solver, and that is equal to 3.46, so pH is 14 minus that, 10.54, so yay! And then that is how you do B. And then last one, probably like the hardest or the most confusing one. And okay, so we have tetraiodylmercury 2 ion with this Kf. Can't really see that that's 6.8 times 10 to the 29th, I think. Yeah. Is the active component of Nestor's reagent, blah blah blah. There's some information to throw you off. And then in the presence of cyanide ion, that ion is converted into the more stable tetracyanomercury 2 ion with this Kf. And now we have to calculate the concentration of the tetraiodylmercury ion at equilibrium given these conditions. And okay, this seems pretty confusing, but first we have to deal with our KFs. And the Kf for the tetraiodylmercury ion, well, tetraiodo, so it's 4 iodines plus mercury would give us this equation, and that would give us a Kf of 6.8 e to the 29th. And then, okay, now we have tetracyanomercury that is really similar. So 4 Cn minus plus Hg2 plus will give us this ion, and that will give us a Kf of 3 E41. And okay, so now we have to kind of move them around a little bit to get things to cancel out. So one thing we can do is just flip this around, so it'll get rid of the mercuries. And so when we flip it, we take the reciprocal of the Kf. So let's just pretend we flip it, and then we cross those out. So we have, nope, okay. And our new K for that, we'll just multiply these two together. So 6 divided by 6.8 e to the 29th times 3e41. And that gives us 4.41 e to the 11th. Okay, so this is our new K, and I'll just underline that. And now we have to deal with the 65 liters of 0.0015 molar potassium tetraiodylmercury and the 32 liters of 0.0064 molar magnesium cyanide. And okay, now for each one, we take the volume and multiply by the molarity, get the number of moles, and then we divide it by total volume, which is 32 plus 65, which is 97, to get the new concentration. So the tetraiodylmercury 2 ion, if we do 65 times 0.0015 divided by 97, we would get 1.01 E93. And now we have to be careful for this magnesium cyanide, because if we know there are 2 cyanide ions in every mole of magnesium cyanide, so we just have to pay attention and just remember to multiply the number of moles by 2 to get the concentration of cyanide. And so that'll give us equal 4.22 E93 molar. And okay, so now I'm gonna use the ice table again, just so it's easier to see. And write down the equation that we made, or not made, but ended up with. We have ICE. Okay, now we can go ahead and write down our I's. And then what we have to find, so what we'll set as X is here, since the question asks us to find the concentration of a tetraiodomercurate ion. And because our KF is really big, it's E to the 11th, we can pretty much assume that this reaction goes all the way to the right. So we can do minus approximately 1e negative 3, and then minus approximately, since it's 4 cyanide ions, it will be 4 times 1.01 e negative 3, so 4.04 e negative 3. And then this doesn't have a coefficient, or has a coefficient of 1, so it'll just be that. It'll just be 1.01 e negative 3. And then since this has a coefficient of 4, we multiply that by 4 again. So plus approximately 4.04 e negative 3. And okay, and then now we do the equilibrium, so we can subtract these two. And that gives us 2.02 e negative 4, and then 1.01 e negative 3, 4.04 e negative 3. Okay, so now we just set up the equation. And again, these two are on top, and then put reactions on the bottom. And then we can solve for X to find the concentration at equilibrium. So and that'll give us 4.35 e negative 10. And so yeah, that is just basically most of the aqueous solution problems from the Princeton test. Cool. Ciao.